let's introduce like first something about vectors, and then we introduce matrices as a transformation between vector spaces. So, linear algebra is about solving system of linear equations as last week we've described. So the main structure in linear algebra is the vector space. So, for example, a vector space could be R squared, and that is basically if we have a vector x comma y, or we write as a column vector, and both x and y are in the real space, real number space.
So like two-dimensional space
Yes.
is R squared.
Exactly. All right. So,
Okay.
and last time we've seen an example of vector addition. So this is the x axis. This is the y axis. We can have like one vector to be 1, 1, 2. Another vector to be 3, 0. And we can actually write it like 1, 2. So this is the endpoint, and 0 is the start point. So this could be a vector of 1, 2. And this is my vector v. And the w3, 0 is right here. Okay, last time we said that when we do vector addition, we basically find a parallelogram and then find the diagonal. So this is v plus w. But we can actually look at it algebraically. So in vectors, vector addition is just to add. So we know that vector v is 1, 2. We know that vector w is 3, 0. And then for vector addition, it's just to add element wise. So it will be 1 plus 3, bottom will be 2 plus 0, and this will be 4, 2.
So vector addition in the 2D, you only add the y's. Oh no, you add both of them.
Yeah.
Okay.
We add x's and add y's. So then we can actually draw this. 4, 2 is actually 1, 2, 3, 4, 1, 2, and it is actually this vector. So adding vectors algebraically and geometrically, the results match. And from there, we can introduce vector space with two operations.
Okay.
Right. So
In terms of, oh, sorry.
yeah.
In terms of what you said about it, like the addition makes sense in terms of space. Um, because I see the algebraic reason, right?
Mm.
Um, like, is it because like what was the other reason? You could
What do you mean?
like just now you said you can see vector addition works in two ways, and then you said one way was the algebraic way, and then I don't know what the second way is.
Oh, it's geometric. So it basically like for two vectors, um, the way we find their sum is to find the parallelogram and then find the
Oh, okay.
diagonal of them.
I see.
The diagonal is the sum of two vectors.
Okay.
All right. But so let's define vector space. So definition of vector space V, we call it a collection of objects called vectors. Along with two operations. Mm. So one is vector addition, is what we just looked at. And the other one is scalar multiplication. So addition is what we just saw, and scalar multiplication basically means, so if I have a vector 1, 2, I'm going to multiply it with a scalar, which is usually a real number, but sometimes a complex number, depending on if you're in the real numbers, real vector space or complex vector space. So for example, if I'm multiplying 2 to a vector 1, 2, then I would get simply 2 multiplied by the first element and multiplied by the second element, and that would be 2, 2, 4.
How do you define scalar, like a scalar element?
That's a good question. So scalars are okay. Uh, scalars are either real numbers or complex numbers.
Ah, I see.
Yeah. So if we define scalars in the real number space, or then our vector space would be real vector space. And if we define scalars to be complex numbers, then we call it a complex vector space. Okay, so defining this vector space, it has some properties. Or we call it axioms of the vector space. So the first one, or the 0th one, is the closeness. It means that after addition and after scalar multiplication, the results has to be inside this vector space.
Sorry, you cut off at the end.
So closeness, it has to be closed under addition. And closed under scalar multiplication. So for addition, it means if we have two vectors u and v belongs to this vector space. Then u plus v should be also inside this vector space. So if I have two vectors, then their sum has to be inside this vector space, or their sum is not defined in the space, and we call it not a closed. We call it not closed under addition.
So it must be inside the same vector space?
Yes.
Okay.
And similarly,
in order for it to be in order to uphold the first axiom, or the 0th.
Yes, exactly. And similarly for the scalar multiplication, if we have a vector v inside of this vector space, then we say a scalar multiplied by this v has to be inside of v for alpha inside of either R or C. Depends on if we're talking about the real vector space or complex vector space. Okay. And that's first axiom, and the first one, that's the 0th axiom, and the first one, or first 4 are about addition. So let's define for all u, v, and w inside of the vector space v. About addition, the first one is called additive commutativity. So it means simply v plus u equals u plus v. So this one guarantees that, for example, if we have 1, 2 plus 3, 4, then it equals, we know that it's 4, 6. And that's the same as if we add 3, 4 before 1, 2.
Yeah.
Right. So that's additive commutativity. And about addition, there's a second property. It's called associativity. It means that for v plus u, the whole thing plus w is the same as if we add u and w together first. Okay. And then the third one is the zero vector. It says that for there exists a vector 0, right? So the symbol is there exists. There exists a vector 0 such that v plus 0 equals 0 plus v equals v. Or we can just write 0 plus v equals v, because we know the first part of the equation guarantees by the commutativity. Right. Then
Yeah.
the last one is called additive inverse.
So is the 0th vector just the origin?
Yeah, you can think of it in that way. Zero vector in vector addition is just 0, 0, all the way to 0. If
Okay.
if we define it in Rn. Okay. Right. Last one is additive inverse. So that means for every vector v inside this vector space, capital V, there always exists a u inside this capture V, such that u plus v equals the zero vector. And this u can be denoted by negative v. All right, these are about additions. So for scalar multiplication, there are other properties.
So these are the only two operations you can perform on vectors.
Addition and scalar multiplication, Yes.
Oh,
Uh, not that you can only perform because there are inner products and stuff, but to define it, uh, but to define a vector space, you only need these two operations.
okay.
Right. So then the axiom of multiplications. Okay, similar to so the in the addition, the zero vector is can also be called a additive identity because you perform zero with other vectors, you get basically the same other vector. So in multiplication,
Mhm.
there's also a identity. And we know that it's one. So one, the number one multiplied by u or by any v equals v itself for all v in v. Similarly, associativity. If we have two scalars, alpha and beta, and we multiply v by beta, and then alpha is the same as if we multiply alpha and beta together and multiply by v.
Mhm.
Let's see distributivity. So it means if we have a scalar alpha and then we have u and v, then we can distribute this alpha to v and then add alpha by u.
Mhm.
So similarly, if we are multiplying v to a sum of two scalars, then we can distribute this v as well. All right, so this is like the axiom that defines a vector space. And we know that, for example, R, R squared can be a vector space.
Mhm.
Let's do examples. And as in the examples above, we just do scalar multiplications and then we do like additions like element wise. But we can broadcast this to all r to the nth power are vector spaces.
Mhm.
So r to the nth power is a vector space.
You just have n dimensions.
Yes.
Mhm.
So basically means um there's a vector space equals r to the nth power, and all the vectors inside looks like v1, v2, the vn, where all vi's are inside some R. Like all VIs belongs to this a set R. That's a real number set.
Mm-hmm. Yeah.
Okay, so um so vector addition in Rn is just if we have Vi plus U, I mean vector V plus vector U, then it's V1, V2, Vn plus U1, U2,
Yeah.
all the way to Un, and that's V1 plus U1, V2 plus U2, all the way to Vn plus Un. So again, vector addition is to just do additions component wise.
Mm-hmm.
And similar for scalar multiplication, we have a lambda multiplied by a v. That's just
Wait, did you say
lambda.
lambda?
Mm?
Did you say lambda?
Yeah,
Oh,
but
like
we
the
can
letter.
do like
Oh.
alpha or beta. It's the
Oh
same.
yeah, no, I was thinking of like I thought of the Python thing or something.
Oh,
Okay.
wait, lambda v2 all the way to lambda v. Okay, so that basically concludes what is a vector space. Do you have any questions?
No.
All right. So, mm, so as a side note, basically all scalars, for example, R in the real the set R satisfies addition, multiplication, closeness, like basically in side note. So yeah, let's just talk about real number space in our course.
Okay.
But all
Because I
scalars,
don't think knot theory needs complex numbers, does it?
right?
I
I
have no
don't.
idea. I don't think so though.
Right. As far as what I read, I haven't seen any complex number yet.
Okay.
Yeah. Okay. So oscillators satisfy following. Okay. So first one is addition and multiplication are closed.
Mhm.
Is addition and multiplication are of scalars are commutative, associative, and distributive.
Mhm.
Third one, zero is the additive identity.
Isn't this just normal math?
Yeah. And fourth one is the
Multiplicative.
multiplicative, right? Means any number plus 0 equals that number itself, and any number multiplied by
Times
1
1.
is that number itself.
Yeah.
So basically, these properties are the definition of a field. So if in the future you're learning math, then this is the definition of a field. Okay.
What's a field?
Yeah.
Just briefly.
Okay. A field is like a mathematical structure that involves these properties, and then we can basically, like, if we know something is a field, then it exhibits these properties and we can use them to prove other things.
Okay.
Yeah.
So it's just a term.
Right. Yeah. So we have like vector space, we have field, we have something called a ring.
Yeah. Sorry. You go.
Other stuff. All right. So basically, and then to prove that a given space is a vector space, we basically go through all the axioms and prove that they're true. But we don't need to do proof in this course, so it's just like a if we're doing it, then this is how we do it.
Yeah.
Right. But if we're proving like something is not a vector space, then we only need one explicit counterexample to one axiom instead of like checking all of them. So one example, because this is how we define vector addition and scalar multiplication, but we can define otherwise. So for example, if we have a space V, or let's say we have a set V, it's V1, V2, where V1, V2 are in R. And we define scalar multiplication to be alpha times V1, V2 equals alpha V1, alpha V2. This is a normal scalar multiplication, but we define vector addition to be V1, V2 plus W1, W2 equals V1 plus W1 and V2 minus W2.
Okay.
Right. This is how we define this operation. All right, now the question is this a vector space?
Oh,
All right.
well, then you need to say it's not, right? Because it doesn't.
Right. So we say it's not because there is some axiom that it does not satisfy. So give examples because V1, V2 can be any number in R. So let's say W is 2, 2, and a V is 1, 1. And then we know that W plus V is by definition V1 plus W1.
2 plus 1, 2 minus 1.
And yeah. and that's 3, and v2 minus w2, that's 1. All right, this is w plus v. However, we know that in vector space, addition is commutative. So let's look at v plus w. And that is 1 plus 2 is again 3, but on the bottom it will be -1. So these two does not equal each other, means it does not satisfy additive commutativity. All right, so therefore V is not a vector space.
Mm-hmm.
So basically in a vector space V, we say the additive identity, which you know 0, is unique. And to prove uniqueness, we usually suppose there are two things satisfy the desired property. And then, and then we prove that they have to be the same.
Mm-hmm.
All right, so for example, in this case, suppose both the zero vector and a zero prime vector are both additive identity. In the vector space. So then by the definition of a additive identity, we know that basically 0 plus v equals 0. Equals v.
Mm-hmm.
And the 0 prime plus v also equals v. Okay, so for any vector, 0 plus that equals itself. So that means if we let this vector then we let this vector to be 0 prime. Then we know that 0 plus 0 prime equals 0 prime.
Mm-hmm.
All right, so similarly, the second equation, if we let this v equals 0, then we know that 0 plus 0 prime equals 0. And also I use the additive commutativity. All right, now I have a thing equals 0 prime and the same thing equals 0. We know that 0 prime equals 0.
Is it not a viable approach to set, like you can't set 0 plus v equals 0 prime plus v? Like, can you approach it that way?
Um, yes, I can, but then I need to say there is no like you cannot find any v that may give you the same answer. So let me think of an example. Mm, but I guess you can in this case because we have that additive inverse. So if you like talk about, okay, I have a 0 plus v, I have a 0 prime plus v, and then v has a additive inverse, it's negative v, and then I add this negative v on both sides, then I'll end up with a yeah, but it would be the same. So if we add a negative v and a negative v on both sides of 0 plus v plus a additive inverse, and we have equals 0 prime plus v plus v, I mean plus the additive inverse. Then what we know is basically these two additive inverse can be reduced to a additive identity, which could be 0 or a 0 prime. So we will end up with the same thing. So we will still have a 0 plus 0 prime equals actually no, 0 prime plus, no, actually no, because we don't know that, we haven't proved, of course it's true, but we haven't proved that the additive identity is a additive inverse of itself. But it's a easy proof, we can do that in a minute. But then we would have this further reduced to a 0, and or we can have this further reduced to another 0 or 0 prime. And then we go to the same thing to do the proof. Right, because like after we define something like rigorously, we can only use what we have defined to do the proof instead of use our like mathematical knowledge.
Yeah.
Right.
Yeah.
Yeah, and that's why there are like jokes about, now you're in the college, you're going to prove that 1 plus 1 equals 2.
Mm.
Right.
Yeah, like in high school, you like they don't care.
Right. Okay, so let's use these. Right. So actually we can do like one more example of to prove that, right, proposition. So this is quite cute as well. We're going to prove that the additive inverse, the negative v, is actually -1 multiplied by v.
The inverse of v equals -1 times v.
Yes.
Mm.
Okay. So actually before that, we have to prove that the so there was another proposition is that the additive inverse is unique. So this is also easy proof. You can do it by yourself, or we can just say this is true. And then we're going to use this to prove the second proposition. So, so as we know that the vector -v is the unique vector such that proof v is the unique such that v plus -v equals the zeroth vector, the zero vector. So then let's now examine the -1 multiply v. So we know that it equals 1v plus -1 v. Because we know that 1 is the multiplicative identity of scalars. All right. This step is by multiplicative identity. All right, then we can by distributivity is we can take this v out and then we do 1 plus -1. This is the first distributivity here. Wait, I mean to say the second distributivity here. All right, so, and then we know that 1 plus -1, we can just do it in the set R or the field R. So that's 0 multiplied by V. And we know that 0 multiplied by V is 0.
I see.
Yeah, from here we know that V plus -1 multiplied by V also equals 0. And we know that this additive inverse should be unique. So therefore, we know that this additive inverse equals -1 multiplied by V by uniqueness of additive inverse. Okay, this is like how to do proofs.
By the unique. And so for the last step, zero.
By definition of zero vector.
Oh, you just subtracted to the other side. Like,
Hmm?
yeah, by uniqueness of
Additive
a zero
inverse.
vector. Oh, additive inverse. No, my bad.
Right. Because the additive inverse should be unique. Let me use this. Because this additive inverse should be unique, that it add the v gives the zeroth vector. So if we have this v adding something else give you the zeroth vector, then this something should be have to be the additive inverse.
Oh, I see.
Mm.
So then, okay, so inverse v has to be zero then if you're adding it. No? Oh wait, no, because that.
Uh, like the sum should be zero, but the inverse v is negative one multiplied by v.
Okay, it's like okay.
Right. So since this additive inverse is unique, additive inverse means to if you add this to v, it gives you the zeroth vector. If you add these to v, it gives you zeroth vector. So it basically means if we have a vector v, then if it add anything that gives you the zeroth vector, we call this anything a additive inverse.
Mm-hmm. Oh, I see. Okay.
Yeah. So then if we have proved that this v adding like something else, it gives you the zeroth vector, then this something else fits inside this bubble, and then it should be the additive inverse.
Yeah, okay, yeah, I see now.
Yeah, right. Good questions. I love your questions.
I just get confused.
Yeah, like
Yeah,
this could
cool.
be very abstract, and many students like first encounter it proves they don't even know like how to ask questions because they don't know what they want to know. So it really like I love your questions.
Okay.
Okay, we good for now?
Yeah, thanks.
All right. So then we've done what we want to do in to define vector spaces. And now, based on this vector space, we are going to find their bases and find like a spanning set. And then basically when we encounter matrices, we can use them to determine, for example, the rank of the matrix and stuff.
Mm-hmm.
So, but to do that, we need to first define linear combination. So a linear combination of some vectors, v1 vector, v2 vector, all the way to vn. And these vectors belongs to a vector space V is a sum of the form alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus plus alpha and beta. And we can write this as sum of AI, VI, I from 1 to alpha, where alpha i's are scalars. Okay, so actually, if you've learned the neural networks, inside of neural networks is like something in this form. So neural network is just about linear combinations if we don't think about the activation function. So so if we have a neural network, and these each of the bubbles is a vector. So basically we have input and then the input is doing it's like performing some operations during the step, and this is the linear combination. And then for each layer there are different linear combinations be done, and in the end we have our output. And basically, in the training process of linear network is to find the weight that we want to do linear combination. So that's like these scalars we are trying to look for.
You're trying to look for like the best scalar.
Yes.
Oh, okay.
Okay, where is these? And now, for example, of a linear combination, if you are in R2, we have a V1 equals, again, 1, 2. We have a V2 equals, wait, next to 1,4. And one linear combination could be so we want some scalar of V1 and we add some scalar multiplied by V2. So for example, if my first scalar to be 6, if my second scalar is -2, then our linear combination would be 6 plus 2 and 12 minus 8. That's 8, 4. And then we call this vector a linear combination of V1 and V2. Okay, after define the linear combination, we can now define basis of a vector space. So we call a collection of vectors v1, v2, all the way to vn belongs to v, called a basis any vector v. Okay, if any vector v admits a unique representation. As a linear combination of these vectors. Okay. Um, mm, basis. So, and that means for any v inside of this vector space, it can be written as alpha 1 v1 plus alpha 2 v2 plus all the way to alpha n. For some unique choice of these scalars. All right, and now these alpha i's is called the coordinates for v with respect to the basis. Hmm.
Because v1 to vn is fixed, right? So the only thing that can change is alpha.
Right. Like if you're talking about this basis, then it's fixed. But there are other bases, so for the same vector space. And that's why we say with respect to the spaces. So for example, one basis for R2 one basis, or the simplest basis could be 1 0 and 0 1. So this is like in the Cartesian plane. 1 0 is like this on the x-axis, and 0 1 is we call this v1, and this is v2. So this is v1, and this is v2. All right, so to represent any vector in this Cartesian plane, for example, this vector right here, we call it v, and
it's 1 1.
Sure, we can do a 1 1, but this one, since I'm drawing like way over here, let's say this is 3 2. Okay, we know it's 3 2, and we know the basis. So basically, this v can be written as 3 multiplied by 1 0 plus 2 multiplied by 0 1. And that's like 3v1 plus 2v2. So since v1 and v2 are the bases, basically we know that the coordinate of v is actually 3 2 in this Cartesian plane.
Oh.
Right. But this is only like, or we one basis, or we call this a standard basis. Right. So, but there are other bases. For example, let's just say if I have a vector W that's 1 2, and we have a U that's 2 0. And now I have a V inside, a V equals V1, V2 inside of this R2. And now I can actually represent this V by W and U. So, so we know that V is V1, V2, and we can write them as alpha 1 times 1 2 plus alpha 2 times 2 0. And that's basically alpha 1 plus 2 alpha 2. I'm just like doing the scalar multiplication and then adding them. And then on the bottom is 2 alpha 1 plus 0 alpha 2. So I'll leave it like this. All right, now we can actually solve for V1 and V2. So you know that V1 equals the top component is alpha 1 plus alpha 2 alpha 2. And we know that V2 equals 2 alpha 1. So basically, you can rewrite, so 2 alpha 1 is V2, so alpha 1 is V2 over 2. All right, now we know that alpha 1 is V2 over 2, and we have V1, so we can rewrite alpha 2 to be V1 over 2 minus V2 over 4. Okay, now, so go back to the definition. So for any vector V, if we can find a unique coordinates or unique choice of alpha 1 through alpha n, then we say this V1 through Vn is a basis. So in this case, we have a unique solution of alpha 1 and alpha 2. So then we say, we know that this combination is unique.
Unique. Are all linear combinations unique solutions? Like, do they all have a unique solution?
No. Like, so if we have unique solution, then we know that our original set of vectors can be called a basis. But if we choose some set of vector that cannot be called a basis, then we would not have a unique solution. We will see example.
Okay.
Maybe next class though. Wait. Yeah, we can do this class. Yes. Yeah. All right. So if the combination is unique, then we say actually this W and U are the set of W and U is a basis of Rn.
It's just because so having a unique combination proves that the set of vectors is a basis.
Yes.
Okay.
But we will introduce to another like definition of basis so that it's like easier to it's more straightforward instead of like going back to see if it's unique.
Okay.
Okay. But all right, we have 3 minutes, but for now we can maybe do a let me see. So a side note on the on some matrix stuff. So last time we've seen a matrix if we have a m by n matrix, and all the entries to be R, like this means we have a m by n matrix with all the entries to be R, in the real number
The
set.
range of
Yes, great. Then basically we know about the sum of matrix to be if A could be inside of this. So we know A plus B, the ijth row and column is actually the ijth row entry of A plus the ijth entry of B. And for scalar, we know that alpha A, the new matrix alpha A ij, the ijth entry is the ijth entry of A multiplied by alpha. Okay, so this is like also a sum of two elements and a scalar multiplication of these two, of a scalar multiplication of element inside of a vector space. So we can say that a matrix, a n by n matrix with all interest in R is actually a vector space with these two operations.
because
And
that's the additive and that's the scalar multiplication. Oh, okay, I see.
yes. And then did you learn about transpose?
No.
Okay, so it's really easy. So it's just we define for a matrix A. The transpose of A uh, written as AT, written as A transpose is defined by the transpose of A ijth entry is the original matrix A ji's entry.
Oh, so it's like across the diagonal. You flipped it across the
Yes,
diagonal.
right. So for example, if we have A to be 1, 2, 4, 6, 3, 7, then the A transpose is 1, 2, 4, 6, 3, 7. So basically flip